Hi, good afternoon, and welcome to the final IDX presentation regarding site design. As we go through our presentation today, please feel free to fill out the comments form below and ask any questions that you may have on your mind. My name is Matt Jarrett, and I'm a student here at Washington State University, and on behalf of the IDX team, we'd really like to thank you for sharing today with our site design process. I'd like to go ahead and introduce our team. The IDX team is actually composed of 2 universities and 2 majors. At the University of Idaho, we have Kate Shrosby, Garrett Gorgon, Nathan Beck, who are all landscape architecture students who have helped us out this semester in designing a lot of the crucial parts of our facility. Over at Washington State, we have Sydney Diekman, Stephen Keith, Ian Smith, Christian Williams, Cody Lane, Anna Martin, and myself, who are all civil engineering students who also put in a lot of time on this project. A little overview of the presentation today. We're going to start off by talking about what we did last fall, which was the site selection methodology for a biofuel supply chain in the Northwest. We're going to talk about the goals of a site design for the supply chain, and we're going to provide you with some of the construction documents we put together for our sample site design. And all throughout the presentation, we're going to talk about how we accomplish the triple bottom line of sustainability, which is economic sustainability, social sustainability, and environmental sustainability. It's important to note, though, from the get-go, that IDX is working for NARA, which is a USDA-funded grant research program, the Northwest Advanced Renewables Alliance. NARA has 5 goals, and first and foremost is to create a plan for companies to be able to implement a sustainable supply chain in the Northwest region of Washington, Oregon, Idaho, and Montana. Along the way of this process, valuable co-products are produced, and NARA thinks it's very important to keep these in mind because they can help offset the costs of the startup of this company. And we have the what down, but the where is also important. NARA's third goal is to help reinvigorate these communities that have experienced recent economic hardships. In line with that, NARA wants to reach out to all these companies and help establish these coalitions in these areas and get companies working together to produce this jet fuel. And finally, NARA wants to increase the literacy about bioenergy. It's an extremely interesting topic, and we want to share that with the common public. The IDX team, as I said before, has been working on the supply chain, and this is NARA's figure for that supply chain. As you can see, it starts at the bottom with forest residuals. These are commonly just thrown away, burned, or ignored, and they're very low in value. With our process, we get it to an eventual biojet fuel, but it's not quite as simple as going from point A to point B. There's mechanical pre-conversion that needs to occur first with the physical breakdown of that biomass. From there, it goes on to pre-treatment, hydrolysis, fermentation, and finally refining to get it up to the point where we can put it in a jet. There are several options along the way to get this done, though. And NARA has looked at several options, but for the purpose of this presentation and this spring's worth of work, we've looked at the liquid depot option, as you can see here, where that mechanical pre-conversion would occur at the same facility where pre-treatment and hydrolysis would occur. This would output a simple sugar slurry that would go onto a conversion plant for final refining, or fermentation and refining. Where this looks like on our supply chain is this area, circled there. As we go through our presentation, we're going to talk about the steps involved there and how to most effectively manage the sustainability of this design. As I said, though, it's about where. And that started last fall when we started identifying potential sites. Well, it is possible to start up a biofuel production facility on a green site. We thought it was more advantageous to look at sites in the 4-state region that already could incorporate parts of the design on their site already. This gave us about 250 sites at the beginning, and we needed to narrow that down. So we went through and identified what's important to make sure that this can happen. What existing things are on these sites that can help us? And from here, we were able to make a decision matrix that would output site rankings. I'll go a little more in depth on our initial steps, because with 250 sites, that's a lot to deal with. So we started with regional values, and we got maps of these values such as biomass availability, port access, social capital, poverty, electricity rates, and others, and we layered them together to give us composite regions of hotspots where more advantageous sites would appear. And right here you can see we circled some of those areas. This allowed us to go from 250 sites down to 30, which allowed us to go more in depth on those sites and figure out some of those specific site unique details. Some of those include acreage, natural gas rates, the presence of wastewater treatment, and the presence of a boiler. When we only have 30, it's easier to look in depth on these and figure out what those sites have to offer. We finally came up with a decision matrix where we have all those various factors like I described, such as the biomass density. All were given a weight, and those weights were arranged in such a way that they summed up to 20. And each site was scored on a range of -5 to +5 on those. The math behind this is that the maximum site score would be 100. With a maximum of 100 and -100 for every site, we can easily see which sites offer more benefits than others. Right here is the final top sites for the liquids depot. I'm going to bring in Sydney Diekman to talk more about our top site and our design.
Thank you. So in our case study, we decided to consider the Georgia Pacific Wanamill site. As you could see in the previous slide, that it was considered by our suitability ranking methods to be most suitable for a liquids depot siting. As you can see on this map, it is located very close to the Portland Airport and also not too far from SeaTac Airport, which are the largest consumers of biojet fuel in the four-state region. As we began the site design process, we wanted to identify the parameters that would come into effect here. First, we wanted to identify the type of site that we would be designing. We selected a liquids depot. After that, we wanted to take into consideration things that would impact site design, such as existing site analysis, the topography of the existing site, the layout of the current facilities, and its location will all impact a case study site design. Then we went into the physical process design. This was where we considered things such as the site layout and process flow, the wastewater treatment, stormwater treatment, and transportation that the site would need. Just to reiterate here, this is the liquids depot portion of the supply chain. So the liquids depot, again, will mechanically reduce the feedstock, put it through pretreatment through the mild bisulfite protocol. It will then undergo enzymatic hydrolysis to produce a sugar slurry, which will be separated so that the sugar can be sent off to a conversion depot. And so these are the processes that need to be considered as we look into developing a liquids depot. Here is an overview of the liquids depot processes. So there's the mechanical breakdown in the wood yard, followed by chemical pretreatment and separation and preparation. Some of the inputs will be biomass, which is the slash coming in, water and electricity used to power these processes, and various chemicals such as sulfur, calcium, and the enzymes used in hydrolysis. The outputs of the depot will be the simple sugars, which are sent on to fermentation, lignosulfonate, which is a valuable co-product that can be sold to help the economic sustainability of such a site, solid lignin, hog fuel, which can be burned or sold as fuel, and wastewater and air emissions, which will need to be treated so that the permits are not violated by this site. The site design considerations begins with the wood yard. This should be located close to the transportation that will be close to where the transportation that will be bringing the slash piles in. So it should be close to the highway and or barges or rail. And then there's also a large area that's required for this 7-day feedstock supply. Then the chemical pretreatment needs an area designated, and it should be located close to the wood yard as well, so that the slash can go straight to the next portion of the process. Near the chemical pretreatment, there should be a layout available for separation and preparation, as this is the next stage of the process. And this should also ideally be located near the end transportation means, so by barge, rail, or road, so that those sugars can be shipped off easily. Transportation needs to be designed for. This would take into consideration traffic flow, as there will be a large amount of trucks coming in every day with the slash. The pavement, so that it can stand up to these heavy truck loadings, and the turning radius and lane width of the roads so that the trucks can get around. Stormwater treatment will need to be considered. The contaminants need to be treated before the water can be pumped into the river so that permits are not violated. Contaminants can come from the wood chip piles, off the trucks, and off the buildings. And then we also want the layout of the stormwater not to interfere with the site design processes. Wastewater will need to be treated as well. There will be a lot of chemicals and a lot of BOD coming off of our process that needs to be, again, treated before entering the river. And lastly, sustainability is considered in every step of our site design. And this is the triple bottom line of economic, social, and environmental sustainability. There's different layers of sustainability in our site design process. So at the highest level here, there's the sustainable product, which comes from a renewable feedstock. Again, these slash piles are otherwise left in the forest and burned, and so being able to utilize these as a sustainable process and produces a biojet fuel that is not made from petroleum. The site selection is also sustainable. We want to limit CO2 emissions, and more importantly, by picking a pre-existing site, we're utilizing existing infrastructure rather than developing off of a greenfield, which is an area where there is nothing there at all. And then the practice on the site can be sustainable. We explored this through wetland creation for stormwater treatment, rather than more traditional stormwater treatment designs. And a pre-treatment alternative was explored as well. Rather than using the mild bisulfite protocol, we considered a mechanical milling process which utilized such equipment as ball mills, air classifying mills, and hammer mills to reduce the wood before sending it on to enzymatic hydrolysis. Economic sustainability was important to our site as well. Here you can see the results of our techno-economic analysis that we performed this semester. And the total to develop a liquids depot came out to about $281 million. And we wanted to highlight that the existing infrastructure is a fairly large portion of this, and by utilizing an existing site, a lot of that cost savings can be seen. And now I'm going to hand it off to Kate to talk about the next portion of our site design.
One of the important factors to consider was land ownership near the site. This is a map showing land ownership within Clatsop County, and there's a large amount of land owned by the state near our site, which is highlighted in yellow in the upper right-hand corner. Owners include the Oregon Department of State Lands and the Oregon Department of Forestry, and as it can be seen, our site is located near a large amount of feedstock, which is ideal for the site's sustainability as a potential liquids depot. It was also important to consider the existing land cover at the site, and this is a map showing wetland areas within and near the site. These wetlands have a role in providing a habitat for resident and migratory species, and as well plant communities. Historically, development and alteration of wetland areas along the Columbia River has fragmented these systems and threatened their health. Wetlands have a role in controlling flooding and reducing pollutants. Water-loving plants sequester pollutants that would otherwise enter the river. So conserving and enhancing these areas supports the health of the lower Columbia River and as well as sustainability goals. Soils also have a key role in the site development. This is a map showing the 3 types of soils found on the site, and the chart goes into detail on the traits of these soils. Wetland areas have very poorly drained soils that are considered hydric and remain saturated for most of the year. Other major soils are well drained, have decent fertility, and are moderately suited for roads and construction. It was important to identify these soil types to choose the appropriate locations in respect to the natural characteristics of these soils. At large industrial sites, such as this, soils with clay or gypsum content are often brought in because they are easily compacted and form the base for buildings and infrastructure. Topography was another major consideration at the site. This is a map showing topography at 40-foot contours, and although it is not the most accurate map for final design purposes, it helps in getting a general idea of the lay of the land. Existing infrastructure at the site is located on the relatively flat areas, and this helped in locating potential areas for a liquids depot because developing on steep slopes requires a substantial amount of earthwork. Another major consideration was flooding. This is a map from FEMA showing the flood zones at the site, and new infrastructure is the most suited in areas outside of these zones. Parts of the current site and the future development may sit in these zones, and this needed to be taken into account for the process. Another major consideration was transportation serving the site. And this map shows the range of transportation modes. There's highway, rail, and water. US 30 runs east from the town of Astoria and west to Westport. There is an on and off ramp that provides access to the site. As well, a single track railroad intersects the site, and this serves many of the manufacturing operations along the river that transport large loads of paper products, wood chips, and lumber. In addition, water is a mode of transportation. There is a barge, and this is used for transporting wood chips. In addition, at the southeast end of the site, there is a ferry that runs from Westport across the river to the town of Cathlamet on Puget Island. Another important consideration was the existing facilities at the site. Georgia Pacific Wanamill owns over 1,200 acres, and these are outlined in yellow. The current operations take up roughly 250 acres of this land, and a future liquids depot would require about 20 acres. This could be located here without significantly impacting the existing facilities. Now I'll hand it over to Ian, and he'll talk more about the site design.
Hi, so now that we've seen the overview of the site and what's around the site, when we looked at the site as a whole, we found that there are two areas that really showed itself as potential for a liquids depot facility. And so you see here the lower site is circled in blue, and the two main things that we saw about that, it was close to the existing facilities and it was close to the existing transportation infrastructure. And those are very important things to be, and so we'll talk about that a little bit later and why that's important. And then in the upper site, you can see up here in the orange circle over here, is that there's a little more room up there at the upper site. And so that plays itself to a little bit more flexibility in design. So those are the two areas that we're really going to be focusing on. And so we're going to take an in-depth look at the lower site advantages and disadvantages. The first advantage is that it's been partially constructed already, and so it's partially developed, and so it's relatively flat in that area, so that's going to reduce construction costs. And in addition to, I talked about that it's close to infrastructure in the transportation infrastructure, so the truck scales, the roads, the railroads, and the river for barge. And so that's going to decrease costs for transportation and bringing in those materials and taking out our end product. In addition, that the site has already been partially developed, so there's lack of forestation on it, as well as there's no on-site ponds, and it's close to existing satellite ponds, which are important for when dealing with stormwater in properties such as that. Some of the disadvantages, and it's visible to local residents. Both sites, you'll see that both sites are kind of that. It's just the way that this facility is set up. In addition, you can see that it's right next to the river, and so it has a close proximity to the floodplain, so you could potentially run into problems with high floodings. In addition, it's far away from the existing wastewater facility, so it'd be a little more difficult to tie in your wastewater into the existing wastewater facility if it had capacity to do so. And then, as I mentioned already, it has less space than the upper site, and so a little bit less flexibility in design when you're designing your facility. And so here's an in-depth a view of the upper site advantage and disadvantage. Unlike the lower site, it's outside the major floodplains, so you don't have to deal with that. There's no interference with existing operations, and so the lower site was right next to the existing infrastructure. However, this is farther away from the existing infrastructure, so there would be no interference for, say, any of the processes going on. In addition, it has a close proximity to the existing wastewater plant, so if we were to tie in our wastewater facility, our wastewater lines to the existing facility, that would cut down on costs for building those wastewater facilities if the existing one had the capacity to do so. It is larger than lower site, as I mentioned earlier, that gives it that flexibility. Has efficient site flow, so any stormwater and wastewater from the processes or raining down on the processes actually have gravity flow down to where we're going to treat it. So that's an efficient site flow. We don't have to deal with pumps or anything with that type of material. And some of the disadvantages are it's visible to local residents. I already mentioned that. Also, it is terraced, so it does have flat areas. However, between those flat areas is very steep. So when you have steep lands, you have to worry about channeling when you're dealing with stormwater, and pretty much just moving water from one area to the other, and worrying about the energy that you have to dissipate before it gets down to the bottom. Some of the disadvantages. Continuing on the disadvantages, is a far distance from the current infrastructure, so you wouldn't be able to utilize a power station if they had a power station that had the capacity to power this facility. It would be difficult to get that energy from the site over to here, to this site. And then additional opposite of the lower site, there is no existing transportation infrastructure close to this area, so we would have to develop those, which would be a higher construction cost. So Cindy had already talked about kind of the overall process flow. So what we want to do is we're going to do the site development, and we did an in-depth site development for both the upper site and lower site. However, to walk you guys through that, we don't want to do it twice for you, so we're just going to walk you through what we did for the upper site. So here again is the overview with the inputs coming on over here, inputs over there, and then the processes in the middle, just the generalized processes. We'll talk a little bit more what's in those processes. And then here's the outputs over here, and so we'll walk you through that here. So the first step is the wood yard. So we're going to bring in the slash from out in the forest, so all those forest residuals, and then we're going to dump those into a big slash pile. You can see the little brown outline there, and then we're going to run it through a chipper, and then that's going to give us our supply of wood chips. And so this is a mechanical breakdown of the biomass. And so the inputs here would be the biomass and electricity for the chippers, and the outputs would be one of our byproducts, which is hog fuel, and that will be going into the power station, which could one of the fuel sources going into the power station that could potentially power our whole facility. And then some of the considerations are the area demands. So you can see the wood chip pile, which is the light tan color, is actually a big portion of our facility, and that is because we have a 2-week supply built up there, and that's just for in case we have any inflow of forest residuals, then we can still have our normal daily operations, even though we don't have as much coming in. The next process is going to take those wood chips in as biomass, and then we're going to do a chemical pretreatment of that. And it's going to be the pretreatment that NARA has put forth, the mild bisulfite protocol. And that utilizes sulfur in the form of sulfur dioxide and calcium in the form of calcium bicarbonate. And that's going to create this liquor that's going to be cooked with the wood chips and then break down the wood chips at the molecular level. What that's going to do is later on in the process, in the enzymatic hydrolysis, it's going to allow for the sugars to be pulled out of that biomass and then be utilized later. And so some of the equipment that's going to be on there is the digester, the flash tank, and blow tank. All standard equipment that you'd find at, say, a sulfite pulp mill or even a Kraft pulp mill. The outputs for this are going to be the lignosulfonate, which is actually going to be a major byproduct of this facility, and it'll actually supplement some of the profits. And so lignosulfonate can be used as a chemical additive for concrete to increase workability. And so that's going to be a major profit for this facility. In addition, things that we have to consider is wastewater and air emissions. Wastewater will be dealt with our wastewater facility later down the road, and then air emissions will be dealt with at each of those pieces of equipment using scrubbers. Other considerations would be proximity to woodyard. We want those close just to decrease on transportation and losses, and then chemical storage. And then so our last step is actually kind of loaded step, is our separation and preparation. There's going to be 2 steps to the separation. The first step will be the enzymatic hydrolysis, and that's where you're separating out the lignin from the simple sugars. So the enzymes will be added, and then that will pull out the sugars from that woody biomass. And so our 2 outputs will be simple sugars and lignin. The second part of the separation is using a filter press to separate the liquids from the solids. So from that we'll get the solid lignin part, which will be a fuel source for our power station again to help power our facility, and then the simple sugars. And then the simple sugars will be in the preparation part. And the simple sugars is really high water content at this point. It's a sugar slurry. And so we're going to utilize evaporators and reverse osmosis and pieces of equipment and processes such as that to reduce those that sugar slurry down to a 50% concentration, water and sugar, and by weight. And so some of the considerations of the lignin byproduct output. That's very important because that's going to be supplementing our profits. And then sugar concentration, we want that to be concentrated because transportation costs are high, and so we want to limit as much as we can to what we're sending out. Enzyme handling is also important because those are sensitive to heat and pressures. And so I'm going to hand this over to Sydney to get a little more in detail of the different designs.
So beginning with transportation design for our site, we wanted to consider the pavement and the parking lot design. The pavement composition would be important, and the thickness so that they can hold up to the amount of truckloads. The lane widths and turning radii, again, to facilitate truck movement. The number of employees corresponded to the parking lot design. We needed to have enough spaces for each employee plus 10%, and also 2 ADA compliant parking spots to comply with the American Disability Act. And then also the traffic volume coming in of the trucks would affect the pavement design. We focused on pavement because the railroad is pre-existing, as are the ports, but the upper site is located in an area that doesn't have paved roads. So these would need to be created for a siting of a liquids depot in the upper portion of this site. The pavement design began by collecting soil information of the site. The primary soils were assumed to be moderately suited for roads, as there wasn't a lot of information on the soils, and this corresponded to an NRCS fair roadbed soil classification. Also, the soils were determined through GIS to be a soil type B, and this is important for the pavement design for the AASHTO design guide process. There was assumed to be 250,000 bone-dry tons per day of slash coming in. This is a design requirement set by NARA for the site. And a design truck with a 6x4 bin was assumed. And at 40% moisture content, this led to 31 trucks per day bringing in slash. So this was the design parameter for the pavement. The ultimate pavement design was a 5.5-inch hot mix asphalt pavement with a 16.5-foot subbase. Now, wastewater was important to design for our site because there are a lot of contaminants coming off our process, and BOD high levels of COD that need to be treated before it can be pumped into the river. The main components of the wastewater treatment are the clarifiers, the flocculation basins, the rapid mix basins, and the aeration tanks. And the volume demands were considered of 2.8 million gallons per day is assumed. The hydraulics residence times for each tank needed to be considered in sizing, and again the BOD and COD concentrations that had to be removed. There were 2 options for wastewater treatment that were considered, and they're mostly the same. They only differ at the design of the aeration basins. So using option 1 to begin, the process starts with a rapid mix tank. This is where metal salts are added to the influent to help facilitate flocculation, which occurs in the next basin. In the flocculation tank, the influent is gently mixed so that large flock particles form. This is important because the settling rate increases dramatically as particle size increases. So the larger your particles, the faster they settle out. The water is then sent to the primary sedimentation tank. This reduces most of the BOD, COD, with BOD being the biochemical oxygen demand and the COD being the chemical oxygen demand, and the total suspended solids, or TSS. But still further treatment needs to be made. The next step of the process is where the divergence occurs. Option 1 considered a complete mix aeration basin. This is sometimes seen in heavy industry wastewater treatment because there can be toxic chemicals that can kill off the bacteria that perform the microbial degradation of the wastewater. So the aeration basin seen here is large enough that the wastewater is dispersed and there's not a high concentration killing off the bacteria. After the aeration basin, the water is sent to a secondary clarifier, which removes the BOD levels down to 20 milligrams per liter and the COD levels down to, I believe, about 30 milligrams per liter, very low. And this is within the permit regulations. The second option is where the aeration basin is a dispersed plug flow aeration basin. This assumes that there is no toxic shock loading to the bacteria, which means that you're not concerned with killing off all of your expensive microbes that perform the microbial degradation. This is a better design in terms of residence time for how long it takes to treat the wastewater, because it takes about 1/10 of the time to treat, as seen with the complete mix aeration basin. Stormwater was another important aspect of site design for our case study. The primary components of this upper site stormwater treatment process were bioretention ponds, sedimentation basins, and wetlands. And this was pursuing the sustainability at the site level. Again, was one of our goals for our site design. The considerations are the design storm volume. We needed to be sure that quantitatively the treatment system was sized to be able to handle the amount of runoff. And additionally, this was really sized for the increased runoff that resulted from development. The assumption is made that the pre-existing runoff, based on what's already currently at the site, is being accounted for by the site's current stormwater treatment design. So we would really just need to treat what the increase is due to our increased impervious area from paving and buildings. We also considered treating the woodyard runoff separately because the stormwater coming off of the buildings and other parts of the site is composed very differently than the stormwater coming off of the woodyard. So they should be treated somewhat differently at first. And then we had to size the wetlands appropriately so that they didn't get too overflowed, which could scour the sides, which would require a lot of expensive rebuilding, or it didn't get too low so that the wetland would dry up. And then the content of the wetland should be made up of more native plants, but plants that are also very efficient at removing such contaminants as nitrogen, BOD, COD, heavy metals, and hydrocarbons. We also considered emergency overflow design, again, so that for that 25-year, 24-hour storm where you see a lot of runoff coming in, you don't ruin the stormwater system by not being able to have an emergency overflow pipe that could divert that excess stormwater. So here's an example of a quantitative design of a stormwater outlet channel. This part is seen at the end of the process. It comes after the wetlands, which treat the water and then diverts the water into the Columbia River. The stormwater treatment system was sized using a 2-year, 24-hour storm design per the Oregon Department of Transportation Hydraulics Manual. This corresponded to a 3-inch design storm, and this runoff volume, again, needed to be considered for the volume of the basins. We were given a preliminary area of the wetlands based on designs submitted by landscape architecture students from the University of Idaho, and then using Autodesk Civil 3D software and the grading and fill functions, we were able to find the corresponding required depths of the basins to handle the volume from that 2-year, 24-hour storm. And this was a dynamic process, so if the ponds weren't quite the right size the first time, they could be resized until an appropriate depth was found. And again, these channels and basins and wetlands treat the added runoff from site development and not necessarily the entire runoff, including the area that was pre-development. And so now I will be handing it off to Kate to discuss the wetland design.
In the design, it was important to address not only quantity of stormwater runoff, but the quality. At an industrial site like this, that activities contribute to significant contaminants and runoff. And here there was an opportunity to address this with design solutions. One major source area included the impervious surfaces, so the roads, parking lots, and all the equipment. Contaminants typical in these areas are the heavy metals, including copper, zinc, and lead, total suspended solids, and hydrocarbons. Other major source of runoff contaminants is the wood chip and slash pile, with common contaminants of BOD, COD, and total suspended solids. So in order to effectively target these contaminants, two separate sequences were used for these two separate areas. And these function as ecological systems to remove contaminants. Pictured here is a swale for runoff from impervious surfaces such as roads. It is designed so that the heavy metal particulates and sediments settle to the bottom, and a vertical pipe allows water to slowly flow to the next stage of treatment. Similarly, for the wood chip pile and slash pile, there would be a separate sediment swale for those contaminants and sediments. After the sediment swale, heavy metals and sediments settle, and this runoff journey continues its treatment. Pictured here is a section that represents a sequence of treatments for impervious surfaces, and it provides an example of how these systems work. At the left is a bioretention basin, and here runoff flows vertically through a layer of mulch and a thick bed of sandy substrate, which filters particulates, leaving the sediment swale. This bed becomes fully saturated, and the water drains to a perforated pipe at the base. This runoff continues its journey. To the right is a horizontal subsurface wetland. And here water flows continuously in a horizontal direction in a bed of gravel, and beneficial bacteria cling to this gravel as well as plant roots, and they transform the contaminants here. When these are designed properly, they can effectively remove pollutants. In an application at the University of New Hampshire, there was an effective over 95% removal of total suspended solids, dissolved inorganic nitrogen, zinc, and hydrocarbons. If a larger storm were to occur, the shallow basin would also serve the purpose of holding this runoff. The berm adjacent to this first stage of treatment separates it from the second stage, where the same treatment is repeated. From here, water flows to what is called a free surface wetland. You can see this to the right and down slope from the horizontal subsurface wetland. Here, there is a series of densely planted marshes, and these are designed to evenly distribute the water. Bacteria grow on the stems of plants and on the soil surface, and these eat the organic nutrients and reduce the concentrations of they eat the organic matter and reduce the concentrations of nutrients. These are designed to provide slow, shallow movement of water so that contact with these natural filters is maximized. From here, water continues on to the open surface wetland, and this is pictured on the far right. Along with all the wetlands, native plantings would be used. This enhances the habitat quality, which improves the biodiversity not only on the site, but for the region as well. One of the goals of the design was to utilize the existing terrain for an efficient and sustainable process, and to provide conservation practices that support the bioregion. These wetlands go above and beyond the regulations and provisioning for stormwater, and we can anticipate that these will become stricter in the future. So designing ecological wetlands like these not only has a role in supporting the ecosystems, but these also work as adaptable systems in the long run. Now I'll hand it over to Matt, and he'll wrap it up.
Hi. I'd just like to wrap it up here by just saying that we composed two designs. You were just walked through the upper side design, but we also have designs for the lower side as well, and both are equally feasible. Well, therefore, the case study of the Georgia Pacific site, we believe that they are adaptable to many sites throughout the Northwest region. We've also prepared a techno-economic analysis that provides insight to the estimated startup cost of implementing one of these sites. Furthermore, we talked about the sustainability of our design from top to bottom. And we would really like to conclude with saying that this process is definitely interesting to all of us. It's sustainable economically, socially, and environmentally. And any company that has a pulp or paper mill in the Northwest could diversify their portfolio by going with a biojet fuel option. We'd like to thank you again for just spending your afternoon with us, and we're going to take a couple minutes to address the questions, and somebody will come in to answer them. So the screen will be playing for a second, but just hold on.
Hello again. So we're going to address some of the questions that came in. And so the first question that came in was, what are the potential markets for the solid lignin and for the simple sugars coming out of the processes? And so the solid lignin actually is being actively researched by many fields for different things. But some of the potential markets would be bioplastics, biochar for filtration, for stormwater filtration or drinking water filtration. In addition to as a fuel source. And so like what we suggested on our site would be a fuel source for the power station to fuel our own facility and to put energy back onto the market. The second question was, and I can flip back to the TEA, was about the wastewater design and if that was added into the TEA in the final costs. And yes, actually it was. And as you see here, it's this dark blue portion down here. And so it's actually a major portion of our costs. But what is what's interesting about that is that this stormwater treatment is actually much larger than the one that was designed in our upper site design. And so this is actually a higher cost than what would be done actually to get wastewater down to acceptable limits. However, this is a full-blown wastewater treatment plant, and so if you were wanting to have different chemicals taken out of those processes, this would be needed. So just to address those two, I don't know if we have any other questions coming in, but we'll come back shortly if there are. Thank you.
All right, so it looks like we don't have any more questions. Again, thank you for joining us today. We will have our construction docs available shortly, and if you have any further questions later on, feel free to contact Carl Olson at WSU. Thank you.